Okay, thanks, Matt. So this is an update on one of the simulation platforms that we use. The last time I gave an update was a couple of years ago, and there's been quite a lot of developments in that, sort of on the platform itself, and then also in the way that we use it. So this is just a run through, but more of a show and tell, really, of how we use Gazebo and some of the features and vehicles that are available in it for people who are interested in using it for simulation, and may not know what's sort of been going on in the background. So the sort of structure of the talk would be like what's new in Gazebo itself. So there's been a couple of changes in that. Then changes that we've done in our plugins, so new features that we've provided, models and vehicles, and then some applications of how it's used. So for those of you who are not familiar with Gazebo, it's a open source robotics simulator, and it's maintained by the Open Robotics team. And this is the same group that looks after the ROS software. So they have a dedicated team who maintain Gazebo, but they also accept pull requests from the community. It has its main features are that it has really precise rigid body simulation. So it's used quite often for doing robotics arms and industrial type robots. It has lots of sensors, so different types of cameras, other types of sensors. They've been extending that to things that we'll cover in a bit. One of the strengths of it is that the simulation server is fully decoupled from the GUI, so it can be run headless, and you can run it on clusters as well. So it supports distributed computing for its physics engines, and that's important if you've got sort of heavy work to do. The physics, the sensors, and the rendering libraries can all be customized or even completely replaced. So it's quite a complicated structure to get familiar with. So there's a very steep learning curve if you want to add another physics engine in or write sensors. But you can modify all of these things. So if you have custom physics features such as aerodynamics or hydrodynamics that you would like to add, it's open. And so you can see how things are implemented, and you can get in there and change it as you need. So what it's good for, multi-body simulation and articulated robots. So if you're interested in how lots of different objects interact or collide, then Gazebo is strong on that. With the addition of extra models for aerodynamics and hydrodynamics, it also turns out to be pretty good for aerial and marine robots as well. And I think in the last talk we talked about doing ship landing, but there's other things you can do with it as well. You can model unusual vehicles, so things that sort of straddle sort of aerial, marine, aerial surface vehicles, or with our hybrids. Because you can just bolt everything together, it's quite good for that, and you can customize them as you need. And if you're looking at interaction between multiple vehicles, probably not swarms. I think it's not designed to deal with hundreds of different vehicles, but in the low tens and things, you can certainly model those fairly well. It's been supported in ArduPilot in various forms since around 2017, I think, and Pierre has kind of did a lot of the foundation work for that, and we've built on that over time. So what's new? There's been 2 new versions since our last update. They give them kind of alphabet names, so harmonic and ionic, and there's another one on the way. The big changes that have been really useful is they've added Python bindings for the messaging and transport layer. So the way Gazebo, different things in Gazebo communicate is through a message bus. And what it means to be able to get them in Python is that you can then intercept those messages and do stuff with them. And we've been using that as a way of getting access to things like telemetry for ESCs, telemetry for other sensors that has been really difficult to do previously. They've made like a number of technical changes. I can quickly drop through them. So if you have a complicated mesh that you don't know the inertials for, you can ask it to auto-calculate that. So that helps you get a more accurate structure up and running quite quickly. And optimization of again, those more complicated meshes. So one of the things that really limits the speed in running simulations in Gazebo is calculating collisions between lots of different objects. So having the ability to automatically optimize complex meshes just gets you up and running a bit quicker. Primitives like cones, so they've just added those. Ideally, to make things run really quickly, you have all your collisions as primitive shapes, and then the collision calculators can run very quickly on those. For people interested in marine vehicles, there's been a lot of development done to add better support for fluids and hydrodynamic models. So there's features like added mass, which is really when you have a marine vehicle moving through the water, there's a body of water around that effectively increases the mass of the vehicle and changes its inertial properties. And incorporating that correctly into the physics model requires some quite deep changes into the way it was dealt with. And that makes it much better for modeling kind of marine vehicles or wave buoys or things like that. And they've been kind of adding entirely new physics engines. So for people simulating robots and things that look like marionettes, where you have lots of articulated joints, there's a simulation technique called Featherstone, which is very efficient for doing those types of models, and they've got an option for that. It's possibly not so useful for aerial vehicles, but the main point is that there's lots of options, and it's very much an alive project that has got ongoing development work. New types of sensors which are of interest to us is things like air pressure and air speeds, altimeters, Doppler velocity logs for boats. So there's support for that. A little bit of work on making the cameras a little bit more realistic. So there's a facility to add lens flare and things like that. So if you're interested in doing computer vision work and using Gazebo as a platform, you can start to modify the way the camera behaves. There's a model which I've not looked at for dealing with lighter near dynamics. So we don't currently have any models for blimps in Gazebo. It would be quite nice to add one. And there is a model to deal with effective viscosity on airships. So that's something that we could perhaps work on coming up. We don't do any space work, I don't think, in ArduPilot yet, but there's a spacecraft thruster model for dealing with that. So I think that's more focused on the Ross space side of things. And then there's an entire environmental sensor system. So if you would like to load a pre-recorded set of environmental data and have a sensor that can read that, so you might have a custom wind field, a custom current field, or something like that, you can create a recording of that data and then define a sensor on your robot that is able to read that as it evolves over time. So quite a lot of flexibility there. And then for the visual side of things, there's some tricks to make the rendering a bit better. So global new illumination, it's a technique where you don't just get the light from the light source, but it accounts for reflections off other surfaces as well. So that's quite an advanced technique. Again, we're not using any of that in the stuff we're doing, but if it became important in computer vision type work to include that, then we could fold that in. One thing they are looking to do is to change their transport from a custom implementation to using Xeno. And I think that's part of future alignment with Ross, and that may be something we're interested in kind of looking at in ArduPilot in the future as well. We currently use DDS. There's been some discussion about using Xeno, but we're not there yet. And then their next version, which is coming out sort of fairly soon, but they're focused on making it easier to use Gazebo for reinforcement learning. And that's important for some of the industrial modeling they're doing. And then, so what have we been doing to complement that? So we've added support for these two new versions into our plugins. There's been a license change, and that was really just a bit of bookkeeping, so that we're kind of more compliant with the way that we're using Gazebo. So that's gone over to LGPL3. And then we've added some features around camera zoom plugins, ability to stream. We've added gimbals. There's work going on to make sure that we correctly suppress servo outputs before the vehicle's initialized, so it doesn't jump around while it's starting up. And there's some kind of work to add extra plugins as part of our GSOC projects as well. And there have been some mistakes that we've fixed as well, things that kind of haven't really mattered until we started solving different problems. So there was a long-standing issue about kind of Gazebo has a different frame of reference for its world. And usually, unless you've got a GPS on the vehicle that has been used in the simulation, it doesn't matter. And we hadn't really been using that up until now. And when we start using it, we realized they were out by a 90-degree rotation. So that's been fixed. And other things, which is really about bookkeeping the structure of complex vehicles. So if you want to feed information from the simulation into the flight controller using our ROS interfaces, the DDS interface, you don't necessarily want to send the entire complicated structure into the flight controller because it's very memory intensive. So we've got ways of namespacing that. So on the side here, you can see this is the transform tree for a rover with lots and lots of joints and things. You're not really interested in most of this stuff in the flight controller, so you can prune that off. Things to make it easier is just kind of reconnecting. So if DDS drops, it reconnects. So there's various other bits and pieces in the Gazebo DDS simulation interface that we've been fixing. And types of things. So there's lots of different cameras that are supported in Gazebos. There's depth cameras, segmentation cameras if you're doing kind of machine learning type operations, wide angle, thermals, depth cameras, and so on. And these are all pluggable into the model. So we don't have examples set up for all of these, but it's fairly straightforward. If you take one of the existing models that has a camera, and our standard model is a Iris quadcopter with a 3 degree of freedom gimbal attached to it. The camera on that, you can just change the definition of the sensor to any of these, or you can stack a whole lot of them side by side. So it's quite easy to equip a vehicle with a range of sensors that can target different things in the spectrum. And we've had questions, so some of our Discord users are interested in actually doing analysis or visualization in ROS. So the depth cameras that we have on board the vehicles, you can map those through into the ROS ecosystem and use the sort of the tools in ROS to visualize things. So this is an example of a depth cloud. They're not the same on the left and right, the same image on the right-hand side. We're looking at kind of a set of primitive shapes and things, but it can be visualized as a point cloud in our viz. So for people, again, doing visual work, that can be handy to have. And so the tools for doing this are not all part of they're not tools that we write. So the ROS-GZ is again an Open Robotics Foundation library, but it allows you to pull data from Gazebo into ROS. But we also use it from pulling data that we generate on the flight controller and publish out through DDS into ROS as well. So there's lots of tools there for getting data into the toolset that you are interested in using. Our camera plugin, we've done quite a bit of work on that because, again, some of our GSOC students had focused on doing camera-oriented work. So camera following and GPS-denied kind of navigation and things like that. So we did quite a lot of work to improve our camera capabilities. So we've added a 3 degree of freedom gimbal, the ability to stream the camera using GStreamer, so you can pull it into like image processing software or put it into your ground control station, the ability to do zooming and things like that. So that's provided a set of tools for developers looking at doing image-based work to get from the simulator. So as an example of this is some of the work I did with one of our GSOC students, Asif. And this was a test environment just to have a look at the initial camera tracking. So what we've got going on here, there's like an environment. So we've created a nice environment with like obstacles and bits and pieces in it. There's an Iris quadcopter circling around the boundary. And in the middle, there's an Omni rover, which is zipping around doing different things. And the 3D camera is locked onto it, and it's doing object tracking. So the copter's moving, the rover's moving, the camera's tracking and locked on using the work as part of that GSOC project. So it's quite a nice demonstration of how everything pulls together. Okay, and so that's kind of changes that we've been doing. Other things are just different models. So there's a whole range of different types of models that we've provided, and we have a library of them. It's part of the those who use our libraries for simulation will know that there's one of the folders in the ArduPilot org called CIDL models, and there's a lot of real flight models in there, and there's a section to do with Gazebo models. And over time, we've just been adding different models into that as we get requests for people to help them out with their models on Discord, and I'll often ask if they want help with the model to put it together and get it working, would they mind us putting it in CIDL models if we get it working as an add-on? And most people are pretty good about that. So as we sort of help our users out, get their models running in Gazebo, our pool of models is growing. So you can see them here. I'll go through them in detail now. Some of them are because they've got specific applications. Some of them it's just because it's nice to have a standard example of a particular type of vehicle. Some of them are just for a bit of fun, really. So the Mini Talon it's just a straight plane, and it came up again and again and again. Why don't we have a straightforward plane in Gazebo? And now we do. So we had really good feedback from the community on putting this together. So like people weren't quite happy with the tune. They wanted the control surfaces adjusted. Tim? VTOL? We have a number of VTOLs. Yes. So there's standard quad planes. There's twin vector thrust belly sitters. There's kind of there's an H-wing, which is pretty tricky to get working actually. So yeah. There's a number of VTOLs. And what's good about kind of the community contributing models is that they're interested in having them work well. So if they give feedback onto them, we can kind of get them tuned up. In the first version of the Mini Talon was pretty terrible, really, and it turned out we hadn't quite got the control surface aerodynamics locked in properly. So we went back and reworked that and retuned it, and it's pretty good now. So I haven't put up all the tuning outputs for it, but it went through an iteration cycle with feedback from users, and it's now operating pretty well, and it's a good starting point for exploring planes in Gazebo. Similar thing with the Aeon R1. Again, kind of people were just after a standard four-wheel diff drive robot. This is something that was it's on our kind of wiki as a model. We now have a digital copy of that in Gazebo, and it runs and operates as you'd expect a diff drive rover to. So if you just want a basic rover that you can kind of test or explore, we now have something for that. One thing which we didn't have support for, and actually I don't think is really available elsewhere in Gazebo, is for Omni rovers, especially those with Mecanum wheels. Then the way that Gazebo and the ROS community deal with this is they have a plugin which sort of mocks it out. So they have a standard sort of four-wheel rover, and then they have something which makes that work by just driving the vehicle in a way that's expected from the inputs that you normally get from ROS, which is command velocity, the way which is like a velocity and rotation. That's not how we tell our vehicles to drive. We just tell them how fast to spin the wheels, and depending on how it's moving, we control how fast those wheels should be moving. So to get that to work well in Gazebo with ArduPilot, you really want the wheels to be doing the physics. So that's what I did. We sort of said, well, take a Mecanum wheel. It comprises a whole set of rollers. Just make the wheel have the rollers. Let the friction and the collision logic in the rigid body system do the work for you. And then we can assemble arbitrary frames that contain Mecanum wheels, and we can run them. So that's what we did. And we have an Omni three-wheel rover that can rotate, move laterally, so it's holomorphic in the XY plane. And as a result of that, we added a new Omni 3 Mecanum model to our rover collection, and we were able to, in developing that, Gazebo is the tool I used to do testing the mixer weights and make sure that was all operating correctly, and then we put an auto test in for that. More standard is the four-wheel rover. So this is fairly affordable frame. So these are kind of a hobby type rover if you're kind of interested in getting up and running on that. And that works. And that was the thing I was also using as a target. These are quite easy to write little scripts for to move around because they behave quite well. And as a follow-up, it would be nice to add external control for this and integration and check that we can actually operate a nav stack with an XY rover properly. For the marine side of things, so Blue Robotics provided a really nice set of CAD files for their Blue Boat. So we took that and created a simulation for it. It's fairly good on the hydrodynamics. So this plugs into a wave simulation I wrote quite a long time ago. Something that I'd like to do with this is provide an ocean floor model so we can attach a sounder to it and some obstacles and start doing kind of bathymetry and other types of things like that. So that's another sort of standard type model that it's nice to have. For fun, the land yacht there, that was kind of part of my entry into the whole world of ArduPilot, doing some work simulating Pete's sailing models. And I needed something I could chase around the beach rather than having to wade into the water to fix it. And so I've got a digital model of the land yacht that runs completely autonomously using the sailing logic. So there was quite a bit of physics messing around to get this thing working. But it works, and it has the same sort of behaviors as the real land yacht. They're kind of an interesting vehicle for sailing because they're quite quick. That means the apparent winds on the sails are quite high, so everything happens quite fast. So it's a good edge case for testing the sailing code, and that's how that one came about. If it was really windy, we could take the land yacht out, but it's good weather for the land yacht is not good weather for operating planes generally. And what's quite nice is that on the back of that, we've got like one of the users on the Discord channel, Andy, had been aiming for a very long time to get his catamarans running autonomously, being able to fly a hull. So we worked together to create a simulation model for that and get that all tuned in and kind of move bits and pieces of the boat around to make sure it was dialed in quite nicely. And he's gone and built one based off the resulting model. And I don't have the video here, but if you look up on the website, you can see he's got it running. So this thing sails up on one hull now, nicely controlled. So that's quite satisfying. And although the match between the simulated and real vehicles, it's not perfect, depending on what you're actually trying to solve with it. And it's often good enough to point you in the right directions about the things you need to deal with in the actual real vehicles. And it helps you get the control dialed in. As you can see, it capsizes, right? So anyone who's sailed a small catamaran knows that they're prone to, like, if you get the balance a little bit wrong, they'll dig the nose in and you'll go over the front. And the model will do that as well. Another vehicle we didn't have, bicopters, quite tricky to tune initially. They require, so this is a copter with 2 props and 2 servos, really twitchy unless all the inertials are right, and quite a long way from a standard tune for this type of vehicle. So they're really twitchy in pitch, and you need to put a lot more on the roll to get them to fly properly. But once you've got them dialed in, they really lock in. So that's quite a nice thing to have. I'm not sure we've used this, but Randy was doing some work on slung payloads. So and I think it was pretty much all solved. But at some point, I thought, well, let's hang a cable with a mass underneath a copter and just see how it behaves. I haven't run all the correction code on this to see how much it damps it down. Pretty sure it'll just be like that when we run it. So you can kind of, and this is an example of coupling different types of objects together to simulate things that may not be easy to write up by hand. We had a really nice GSOC project from Pedro. and which was on copters and integration with the ROS2 nav stack. And this is an extension of it to rovers. So this is kind of your standard sort of get familiar with the ROS2 nav stack with a rover type setup. But instead of using ROS to control the vehicle, doing the kind of the low level control, we're using ArduPilot for that instead. And it integrates Gazebo, ROS, ArduPilot, nav stack all in one go. It works really well for Humble. They've made a lot of changes in the recent version of ROS, and we're not quite up to date with that, so we have a little bit of work to catch up there. Another application of like a real vehicle going into being modeled in real life is Nate's work on the weight shift control aircraft model. And this is like an amazing vehicle. And it was very impressive. Like Nate put it all together and we kind of like fine-tuned the model just to get the initial version, and then he went off and ran with it. And I believe that's been really instrumental in helping them get the real vehicle working. And they've done things like taking data from the real vehicle and replaying it through Gazebo to check kind of the accuracy of it. And the lineup's pretty good, and it's certainly good enough to like make it work. I think these are notes kindly given to me by Nate, but I think kind of saying that they had after getting the prototype and simulation run up, they only really needed 9 real flight tests to get it working. So that's a good story. So if we can do things like that, then that helps people speed up their development process for certain types of new aircraft. I mean, there are aircraft where the aerodynamics in Gazebo are not going to be the right thing. So, but for some of them, it will be. And I'm not going to talk a lot about this at the moment. But some work that I've been doing with Ryan on looking at kind of terrain planners for planes. At one point, I wanted to run some examples in Gazebo, so we needed terrain models. And there's kind of a workflow for adding terrain to Gazebo examples. And you kind of there's a kind of like it started out as a game engine, I think, but they've got the ability to snapshot their tiles. You can import the height maps into Gazebo and overlay an image on it, create a terrain map. And it's not very detailed, but it's good enough if you're after a bit of rough terrain to then sort of see if you can fly your play around it and avoid bumping into things with the algorithms that you're running. Okay. One thing that's come out of this that's been really great, and then we're going to, fortunately, I don't have your tool up and running because I put this together before then. But for a long time, it's been really hard to get sensor data out of Gazebo. DroneCan is a really nice solution for that because you can push, and that's where the Python bindings come in, you can push data from Gazebo into DroneCan, and once it's there, it looks just like a normal sensor. So all the existing backends that work for that particular data type that are already available in ArduPilot just work. So as far as the flight controller is concerned, it's not looking at a simulation, it's just looking at a supplier of a type. And so if you want to move between real and simulated vehicles, that can set up for that particular sensor is the same. Yep. Yes, when we have the feeds from them. So that's some work. So in this case, I just have an EC, but I don't have position data coming through. That would be something we could look at adding. The one thing I have added is NatSav data. So forever, we've not been able to get GPS data from Gazebo into ArduPilot, and now we can. Now it's really easy to do that. And so you can kind of line up the two sources of GPS data, you can fail one and see how that works. So all of a sudden, we've got a whole set of data that Gazebo can generate that we can pipe into our simulation and use them as just, they appear just like natural sensors. And you don't have to write any work, do any work on the flight controller side because it already has the back end. We have about 5 minutes. Yeah, okay. So quick summary, and I'm not doing a service to all our GSOC students. We have really, really good GSOC students who do lots of interesting things. And a lot of them have been using Gazebo in some way or another for their projects. And here's a summary of these, kind of typically vision type projects where you've got kind of craft and vision and you need to kind of integrate all of that. So GPS denied, high altitude work, follow me. And this year we've had someone working on our motor plugins, so we can actually get sort of a proper motor model into the library that consumes battery and will give telemetry back out through DroneCan, so we can start modeling battery consumption. So that's that. Now, for the last little bit, this is kind of it cropped up because we had a user asking how to get control of a interleaving tandem dual helicopter, and they were asking how to do it. And it sort of piqued my interest because I thought, well, we've never really tried to model helicopters in Gazebo. They're kind of quite difficult to do. There isn't, as far as I know, a really good helicopter model in Gazebo. And the usual approach for these is to construct a model for the entire rotor disc using methods such as blade element momentum theory. And that handles the whole rotor, and all you get back from that is just a thrust, a sort of a force and moment to apply at the rotor shaft that drives the vehicle. And that thing has to collect all the stator. So they're quite complicated to write and get working well. And I thought, well, maybe we could try a different approach. And how about we let the rigid body system do most of the work? So to start with that, we needed to fully articulate the swash plate, the rotor head, and all the blade hinges. And then I'm going to just say, I'll apply a really simple lift drag model for the blade, the one we've already got and we use on our other vehicles. Does it work? So let's have a look. So the hardest part is getting the rotor head to work. So physics engines are really good for things that look like marionettes. As soon as you connect one part of the system up to another one, you have a really complicated constraint that you have to maintain. A rotor head has lots and lots of these things. So it has lots of what are known as closed kinematic chains. And what that does is, for people familiar with kind of matrix systems, when you have a matrix system that is not linearly independent, that becomes singular. So if you try and solve a problem with that matrix, it either won't get a solution, or it'll be very badly behaved, or you have techniques where you have a bit of the problem that could go off in any direction you like. So they're quite hard to control. And the rotor head is just such this problem. So when you throw one of these things into a simulation, it's really hard to get it to behave properly. Most of the time, it just wants to shake itself apart. So as you speed it up to operating speed, it vibrates more and more. So the big problem in this was actually getting the joint constraints to be tuned properly. And it turns out one of the advantages of Gazebo is you can burrow all the way into the physics libraries and modify the things that the physics engine is using to control those types of things. In this case, they're kind of like the forces they apply to push the joints back into place and how much effort they spend trying to do that each loop. And if you do that, you can get the thing to be stable. So the rotor head, you can solve it. And the nice thing about that, that's how we drive a helicopter. We drive it with three servos. We adjust the cyclic and collective on the swash plate with 3 servos. And if you have this, then it's easy to plumb ArduPilot into the rotor head. And then the next part is like, what do the rotor blades have to do? And it turns out, so the swash plate gives you the feathering or the variable pitch in the rotor blades. And it's not enough to just control the blade pitch. You have to let the blade hinges flap as well. So on the Align helicopters we've got there, I think they kind of like pivot like this, but in general, you can allow the blades to flap up and down. That's not actuated, they just move of their own accord. So if you apply a force up on the blade, it'll want to lift up. The centripetal force will be trying to flatten it out, and it'll balance somewhere in between. And the thing that controls how that works is where the hinges and how far it is away from the blade. And it turns out, did I cover it here? Aerodynamics. What that does is, if you imagine the rotor disc can deform into a cone, and then that whole cone can tilt forward and tilt round. And it turns out, because it's a spinning system, if you apply the force here, it doesn't tilt up there, it tilts up or down half a cycle later. So that there's a phase lag between where the blade flaps up and down and where the force is applied. And the size of that phase lag is controlled by the distance of the hinge. So, and that's something that these BM models have to model. And it turns out if you just do the rigid body physics, you get all the same behaviors. So that's quite good. And it's crucial to have that. Otherwise, you have no yaw control and you don't have the thing operating properly. So for the airfoil, really simple airfoil, piecewise linear fit to NACA, symmetric airfoil. So it's the simplest aerodynamics model. You have lift drag at one point on each of the rotor blades, and that's it. So does it work? Somewhat surprisingly, yes, it actually does work. The helicopter flies, it hovers, it has plausible behavior. You get the correct lags between the various kind of motions that you'd expect. And with all the tools we've got about, with the monitoring tools for drone can and things, we can pipe all the telemetry out of this copter into the flight controller and then watch it. So you can study the behavior of this thing as it works. It's not a proper helicopter model, but it's a plausible start for future improvements. And then someone said, well, does auto-rotation work? So the answer was initially no. So here I'm using Matt's early cut of Matt's auto-rotation branch. There's a better version now. And initially it didn't work. So you sort of build your custom version of Fiddle and put auto rotation on, you switch in auto rotation, and it falls out of the sky because you realize the first thing is the motor must be able to freewheel. And if it was velocity controlled, you switch the motor off, it locks it at 0 and it's off. And the second thing, this has got a direct drive fixed pitch tail rotor. So if you don't make that reverse, then you've lost all your authority because you can't drive the motor. Once the torque on the main rotor's not being driven, a single-sided direct drive fixed pitch tail rotor isn't going to give you your authority. So you have to put a reversible tail rotor in. You need a rangefinder to find out how close to the ground you are because the flare calculation needs to know that. And all of these things can be fixed because it's an open source. You can go and customize the joint control. You can allow sort of reversible tail rotors. You can add a LiDAR sensor, and then you can use DroneCAN to pipe all that stuff through to the flight controller where it needs to know about it. And it auto-rotates. It's not perfect. It's still got like sort of pitch control, but you put the helicopter up, you drop the main rotor power off, and you switch it into auto-rotate. It curves around onto its kind of target auto-rotate flight path, wobbles its way down, and lands. So yeah, it kind of works surprisingly well for a model that has the most basic lift drag aerodynamics. So I think we could do a lot better with it, but it's already doing quite a lot. And back to the original thing that drove that, which was the interleaving dual helicopter. So there's a counterclockwise and clockwise versions of the rotor head, and if you put two of them on a vehicle and you tell it that it's going to be a Arduino interleaving helicopter, it will fly auto missions, it will do those sorts of things. So it's a kind of an area under progress, but there's quite a lot you can do with a rigid body dynamic system with a little bit of aerodynamics added over the top, and quite a lot of fiddling around. That's it for me. So questions, anything like that? Nate? Sorry? Yes. Yeah, he was the one who suggested that I needed to put flapping hinges in to get the rotor cone behavior. And yeah. Ryan? It's a LiDAR sensor with a narrow cone. So that's all it is. And then you just pick out that, and then I think I've got for this one, I think I've got a Python script where I'm mapping that into one of the rangefinder drone can types, and then just publishing that back out.
Thank you for joining us for the Arduino Pilot Developers Conference 2025. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, QPilot, High Tech, Polybro, IR Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus. Organised by KH Unmanned. Hosted by 3DXR in North Yorkshire. Broadcast by Q Branch.